So the premise of all of these sections is about the conic sections. These are all kind of related to the conics. So we had that picture at the beginning where we showed how if you cut into the cone at a different angle, you get the different shapes. All of them really do have practical applications in real-world kinds of things. I talked about the ellipse, where the sun would be at the focal point of something orbiting the sun. With a hyperbola, as it turns out, things that come into our solar system but are coming through fast enough that aren't caught by the sun's gravitational pull would come in, and they actually follow a hyperbolic path. There's a lot of things that behave that way. And I didn't draw that very well. This would be more like, put that down. Be more like up here, where that focal point would be like the sun, and the thing would come in, and it would come in and just kind of get bent around the sun and then continue on out that path. They do, years ago, 2006 maybe, they launched a probe to go to Pluto, and it's like getting there this year. I actually remember watching the thing launch. Okay, 2015, that's forever. And so, but it's getting there now. It's finally getting there. But one of the things they do that's kind of cool is they do this gravity assist, where they will send the probe, and I think it was behind Jupiter. So as Jupiter's coming along, they send the thing towards Jupiter, and it goes around the back side of it, and it bends it a little bit, kind of sort of gets caught in its gravity. But what it does is, as it's coming in, it helps it to pick up speed, and it ends up going out past Jupiter faster than it was going in. So without having to use rocket fuel, which is really heavy to launch, they're able to get this thing on a much faster trajectory to get out to Pluto. So it took a lot less time by doing this gravitational assist. Same kind of a thing. Comes in and bends around it. All right, so when we did the ellipse, this is the ellipse picture. That's an ellipse, by the way. Hopefully we knew that. When we did the ellipse, what we saw, remember when I did the string on the board, that no matter which direction I went, if I went here plus here, that those two distances always added to the same thing. The two distances added up. But with the hyperbola, instead of it being an addition problem, it turns out it's a subtraction problem. If I can get the page to advance. So, totally different picture. I know this is like a blob looking to you right now, but let me help you see what's going on. That if I pick any, I still have two vertices, not vertices, focus points, two foci. And if I pick any point and take one distance and subtract the other distance, that will remain a constant, just like with the ellipse. So in other words, this distance minus that distance is the same value. This distance minus that distance is the same value. One of the things that's different about this is, let's say that when you subtract, I'm making this up. Let's say you subtract those two numbers and the answer is 10. Well, I could do 11 minus 1, that would be 10. I could also do 8 billion 10 minus 8 billion. That would be 10. So in other words, the point is, you can go way out past the end of my graph here and way back in to this point, and the subtraction would still end up 10. With the ellipse, it was just this little area where the two things could add, and again, I'm making up the number 10, but there were two numbers where this length plus this length adds to 10 is pretty narrow, because they have to be positive values. There's fewer points, even though there's an infinity number of points. But here, I can go way out and still get that number. The point is, the hyperbola has arrows on the end. It extends out forever, both directions. All right, so let's talk about this thing. The generic look of this is really similar to the ellipse. The only difference is what? The minus sign. So we talked about that little flow chart. We looked at that flow chart a little bit the other day. Did we talk about that? Yeah. Yeah. Yeah? Yeah. We talked about the flow chart. One of the things, glance back at your flow chart. One of the things we looked at on there was the idea, you look at the square terms. Well, there's two square terms. But one of the deciding lines at some point was, do they have the same sign? And in this case, they won't have the same sign. One of them will be positive, one of them will be negative. When they have different signs, you're going to have a hyperbola. Just the way it works out. When you got different signs, it's a hyperbola. Everything else about the equation looks exactly the same. One significant difference, though. With the ellipse, we all know that 2 plus 3 is the same thing as 3 plus 2. It doesn't matter what order you add things in. But with the hyperbola, because it's a subtraction problem, it makes a difference. The order in which you write them matters. So in this first one, the x value is coming first. In this one, the y value is coming first. When that's the case, again, subtraction, so the order matters. When the x value comes first, that's going to be a hyperbola that opens up sideways. When the y value comes first, it's going to be opening up or down. Now, the way I think of this, although it probably won't read it anywhere in the book, but when the x comes first, it opens up in the x direction. When the y comes first, it opens up in the y direction. Y direction is up and down. X direction is back and forth. So that's one of those, nothing magical about that. It's just, and I've talked about this all the time with formulas. The formula is great. They do all the work for you. You just got to know the formula. So when it's in this form, this is how you can interpret the information. So we got two different things going on. Now with the ellipse, it was stretched farther one way than it was the other way. And that was based upon which of these numbers was bigger. That's not what determines in this case. It doesn't matter which of these is bigger. The smaller number could be first. The smaller number could be second. It doesn't matter in terms of which direction it opens. What determines that, well, this isn't what determines it, but how you can distinguish it is which variable comes first. So this is a hyperbola. The center would be, you read it off exactly the same as you did the circle kind of information. The center was it would be at 2, 3. Now here's the place where a lot of people screw this up. When the y comes first, we're so used to saying x on the left, y on the right, that when you write it this way, a lot of times people say, oh, the x value is 3 and the y value is 2. It's with the number that it's with. The 3 is with the y. That's puts the center, the y value of the center at 3. The x value of the center is at 2. Now, if this was an ellipse, we would think, okay, in the x direction being stretched 4, in the y direction being stretched 5. But it's not an ellipse. But it's going to behave very similar to that. So what we're going to do is plot this kind of like it's an ellipse. Everything about it starts off that way. So I found the center. Center's at 2, 3. So here's the origin. It's a little hard to see. That's why I put a dot there. That dot's just to help us see where the origin is, because it's hard in this graph. So I went over to 2, 1, 2, up to 3, 1, 2, 3. There's the center. So remember what it said. Back up for a second. Stretch it 4 units in the x direction and 5 units in the y direction. So that's what I did. 4 units in the x direction. 1, 2, 3, 4. 1, 2, 3, 4. 5 units in the y. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. There we go. Now here's where things change. Around that center point, we're going to now create a rectangle. And as it turns out, there are, with a hyperbola, there are asymptotes. And the asymptotes are simply the diagonals of that rectangle. There are asymptotes, and the asymptotes are the diagonals of that rectangle. The rectangle is not part of the picture. The rectangle does not belong there. But we're going to draw a rectangle because it helps us figure out where the picture is. We use the rectangle as a way to find the asymptotes, and the asymptotes help us figure out where the hyperbola goes. Now let me say there's 1,001 things we do with hyperbolas. We get into great detail. I think our goal is to develop a little bit of an understanding, be able to kind of play around with some of the equations a little bit, have a little bit of background on it. Be able to recognize that something's a hyperbola. Occasionally in calculus, the equation of a hyperbola will come up. I'm going to back up a couple of slides. Y value came first. Because the Y value came first, this graph's going to open up in the Y direction. So, back on this picture, I drew in the asymptotes, and the hyperbola opens up and down. These points, this one and this one, because the Y came first in the Y direction, those become the vertices. There's only 2 vertices with this graph. There's only 2. Just like with a parabola, parabola's got 1 vertex. But this one's got 2 because there's an open up branch and a downward branch. So we use the diagonals. Oh, didn't want to do that. We use the diagonals as reference, and I use these 2 points. Those are the vertices. So I start here, and I have to curve out and hug along that asymptote. I have to start there, curve out, and hug along that asymptote. Likewise on the other branch, start here, hug the asymptote, hug the asymptote. Now, one of the questions I'm going to ask you is, find the equations of the asymptotes. There's a little simple process to this. This is one of those pieces people miss all the time. Focus in here for a second. Because once you see it, I think it's easy to understand. Look at this line. I have this point, and in order to find the equation of a line, I need a point and a slope. I need something about the slope. The slope's real easy, though. I found this line when I drew this rectangle. Oh, went too far. When I drew this rectangle, but look at how that's not what I wanted to do. Go away. When I drew that rectangle, I went up 5 and I went over 4. That's what I'm trying to show you in this picture right here. To get the sides of the rectangle, I did the stretching, right? Stretching in the Y direction, stretching in the X direction. So I went up 5 units and over 4. That's the slope of that line. 5/4. Likewise, though, I went down 5 and over 4 also. So one of the lines is going to have positive 5/4 slope, and the other one's going to have negative 5/4 slope. These numbers came straight from the equation. Look at the equation you wrote down at the beginning. Underneath the X value was 16, yes? X is, think about rise over run. Rise is the Y values, run is the X values. Underneath the Y squared was a 25. So when you glance at the equation, you should be able to tell me the slope of the asymptotes. Look underneath the Y, that's the rise. Look underneath the X, that's the run. It's right there at the very beginning. Now you can get that from the box, rise 5, run 4, but you can get that from the equation. The great thing about equations is they do all the work for you. The bad thing is you've got another equation. Once you figure out what this stuff is, though, it's really easy to read it off. But, where's the origin on this thing? Right here, right? Neither of those through lines go through the origin. And this would be the equation of a line that goes through the origin. through 0, 0, right? Y-intercept is 0. Well, way back at the very beginning of second quarter, maybe, I don't know, somewhere in there, we spent a ton of time talking about translations and transformations. Like when I do y equals x squared versus y equals x squared plus 3. Is this 3 in with the x? It's out with the y. If it's out with the y, it affects the graph in the y direction. Does it do exactly what it says or the opposite of what it says? It does the same as what it says when it's outside, when it's not in with the variable. When it's in with the variable, if I did minus 2 in here, that would shift the graph to the right 2 units. Okay, we spent a ton of time doing that. And one of the reasons we did is to make it easy to understand this. This equation is an equation as if it were at the origin. If this graph was at the origin, I would be done. But I'm going to go way back here for a minute. Way back at the beginning, this is not at the origin. It's been shifted to the right 2 units, and it's been shifted up 3 units. So what I need to do to the equations that I have for the asymptotes, let me go back to where I was, is I have to shift them in the exact same way. So what I'm going to do is I'm going to take out this x value and replace it with the exact same shifting that the graph got shifted. Look at the original equation. It says x minus 2 in parentheses, right? Not just x. It says x minus 2. So on this equation, I'm going to take out the x and put in x minus 2, the exact same one that the original equation has. So what that does is shift my graph to the right 2 units. But I also need to shift it in the y direction. So I replaced this y with, look at the y value in the original equation. It doesn't say just y squared, it says y minus 3 squared. So I take out the y and I replace it with y minus 3. And then simplify. So I distributed, I have to add 3 to negative 5 halves. 3, by the way, is 6 halves. So negative 5 halves plus 6 halves is 1 half. Yes? I'll come back here in a second. I want to go back for a second. Look at the equation. It's supposed to have a 1 half y-intercept. Look at the picture. Right there. There's 1 half. That's where it's intersecting the y-axis. Let me do the other one. The exact same thing. I have to have one that has a positive slope and one that's got a negative slope. So over here, I did the negative. And you have to do them separately. Let me say that again. You must do them separately. You can't do the plus and minus and then at the end change the signs. So, everywhere I saw an x, I replaced it with x minus 2. Everywhere I see a y, I replaced it with y minus 3 because that's what the original graph did. It got shifted in the exact same way. So shift my asymptote in the exact same way. Distribute. Now I got positive 5 halves instead of negative 5 halves. Now when I add 3 to that, which is 6 halves. 6 halves plus 5 halves gives me 11 halves. One of the questions I will ask you is, what are the equations of the asymptotes? That's the answer. Let me take a deep breath there. Questions. Which part of that made you, And maybe there's not enough to actually ask a question, but you want me just, can you say that part again? Notice the y-intercept, 11 halves. That's 5 1/2, right? So let me go back to the picture for a second. This negative one should have a y-intercept of 5 1/2. So here's the origin. So here's 1, 2, 3, 4, 5 1/2. It's right where it's supposed to be. Foci. That was asymptotes. Foci. Second piece of important information in the category of what's the important information about the ellipse, or what is this, hyperbola. One of the pieces is the vertices, the coordinates of those points. Another piece is the equation of the asymptotes. And another piece is where are the focal points, the foci. You still have focus points in this. Notice the difference. Remember with the hyperbola? This is a hyperbola, saying them backwards. Remember with the ellipse? It was a squared minus b squared because it had to be shorter. The focal points had to be on the inside of where the vertices were. But with the hyperbola, the focal points are beyond where the vertice is. Here's the vertice, and the focal points are beyond that. They're farther away from the center. That's why this is a plus. Ends up being a squared plus b squared. So in this problem, underneath one of them was a 25, underneath one of them was a 16. Add them together, 41, square root of 41. Square root of 41 is going to be 6 and some change, right? Somewhere between 6 and 7. I don't need huge precision, just ballpark kind of thing. So if I were graphing this, I would go, now, remember how this opened up and down? So what I need to do is go up and down the square root of 41, which was 6 and some change. So from this center point, I'm going to go 1, 2, 3, 4, 5, 6, and a little bit. I don't need huge precision, just kind of get me in the ballpark. Can't be more than 7, can't be less than 6. It's got to be somewhere in between. And so look at how I wrote the focal points. You're going over to 2, and you went up that from 3, and down that from 3.
Is there a triangle?
It comes sort of. With the ellipse, there's a relationship in the ellipse between these points, and you could do a triangle here and kind of find a thing there. Blah, 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 because that's sort of. I'll leave it at that. I don't want to confuse the issue. I'd have to spend some time kind of thinking through. But it is kind of like a Pythagorean theorem thing. All right, that's all the pieces. That was a lot of stuff, I know. So, generic equation. I'm going to tell you, it's a hyperbola. Put it into standard form. Find the center, vertices, foci, and equations of the asymptotes. So that's the important stuff for a hyperbola. This is exactly the kind of question you'll see on a test or quiz from. Exactly like this. All right? I'm going to give you a little head start, and then we'll work on it together. Key things that can really screw you up here. A couple of things that we have to be careful about as we go through this. So first things first, I recognize that it's a hyperbola. I want to put it into standard form, so what I'm going to do is put all the x's together, put all the y's together. And so the question about which one comes first, I'm going to put the one that comes first, or the one that's positive first. And we're going to be subtracting in the second one. So got those together. Now, to complete the square, I got to have the leading coefficients be 1. So first thing I'm going to do is factor out. Here's the big oops, number 1. When you factor out a negative 9, Meryl, what happened? The sign changed to positive. So, sign changes to positive on the 8. That's a big deal because that's going to mess up where the center is, if you got that backwards. So, half of 4. Half of 4 is 2. 2 squared 4. So I'm going to put a plus 4 here, but what did I really just do? I added 100. So to the other side, I'm going to add 100 in a minute. Likewise, over here, remember the sign changes. Half of 8, 4. 4 squared is 16. But here's the big screw up on this one. Screw up number 2 that's really easy to miss. What I just did by putting a 16 in there, 16 times 9 is 144, but because it's minus 9 on the outside, what you really did is just subtracted 144 from that side. So since that's equal to negative 144, I got to do negative 144 on the other side as well. Did that change anything, Mike? Okay. And that's just one of those, oh yeah, forgot things. It's real easy to miss that. I'm telling you now, not all the ones in the book, but probably ones I'm going to give you are going to work out nicely. It is not an accident that 9 times 25 is equal to that number. Not all the problems in the world are pretty happy, working out lovely, perfect squares. But to help us get to the place where we can begin to see the patterns, I'm probably going to give you ones that are pretty straightforward. So, it's not in the right form. If you think about what the standard form is, it's got to say equals 1 over here. So I got to take both sides of this equation, divide by 225, boom. The nice thing is, that goes in evenly, that goes in evenly. And we end up with those guys. Now, be careful. You can't just automatically say, oh, with the y there's a 25, that means underneath it at the end, it's going to be the 9. Okay, yes, but no. Don't start trying to shortcut it. All right, get yourself there through the process, because they don't all work that way. In which direction does this open? Left, right, or up, down? Up and down, because the y's come first. The center is at -4, 2. Keep in mind, x is with the x, y is with the y. It's real easy to think, oh, x's are always on the left and the y's are always on the right. It's not in this case. They're reversed. Without doing any work, I can tell you what the slope of the asymptotes are without even getting the graph. Remember, in the y direction, that's the rise. This one's the run. The square roots of those numbers. Rise over run. So it's going up 3 and over 5. Positive and negative. But that's if it were centered at the origin. It's not centered at the origin. It's centered here. So I need to do the same shifting as the original picture does. So I got to put those values in for the x and the y's. See how that's working? How that takes those simple lines that would be at the origin and moves it over to the left 4 units and up 2. You can't just distribute the positive 3/5 and then at the end change it to plus and minus. You have to do them as 2 separate problems. You have to do them as 2 separate problems. And I've said that 3 or 4 times now, and I'm convinced that there will be 1 or 2 of you who will do them as 1 problem and at the end just try to make it plus or minus. It just doesn't work that way. Because you have different y-intercepts when the lines cross over somewhere else. And if you do it the other way, you'll have the same y-intercept, just as different slopes. So you have to do them as 2 separate problems. Distribute. That's where the 12/5 comes from. One of them's plus, one of them's minus. 2 is, when I add 2 to both sides, in fifths, that's 10. Darn. That's 10/5. 10/5 added to both sides gets me those. Nasty numbers. You are not going to be able to look at an equation, look at the graph, and figure out that 22/5 is the y-intercept. You're going to have to figure it out algebraically. Now, one nice thing you could do is if you were to graph those 2 on your calculator, you should see them crossing at the center point. Those should cross at that -4, 2 point. Excuse me. All right, so graph it. -4, 2. Here's the origin over 4, up 2. Make the little box. X direction, it's getting stretched 5 units. Y direction, 3 units. So over 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Up 3. 1, 2, 3. Down 3. 1, 2, 3. There's my box. The box is not part of the answer. So if you draw this little box, make it really light, or maybe make it dotted or something. It's not the graph. It's not part of the graph. But we use it as a reference, as a guide to figure out where the graph goes. The diagonals then should fit in there. The equations you have should be right through the center of that rectangle. And then you have to hug along the asymptotes and go through those vertices. We knew it opened up and down, so there's the vertice, those are the vertice. This point and this point aren't anything. They're just kind of there to help us figure out where the box goes. They're not part of the graph. So if you really wanted to, you come in here and take all of this stuff out of there and just have that. That's the answer. Leave the stuff in there. You don't really need to erase it. Just leave it in there, but I'm trying to emphasize that the rest of the stuff is just kind of tools we use to get there. So, got the picture, got the asymptotes, got the vertices. What I need is the focal points. And so the focal points, it's a squared plus b squared. Take the two values, add them together this time. So because this thing opened up and down, in the y direction, I'm going to add square root of 34 to the y value. Square root of 34 to the y. Add it and subtract it. Now, to graph it, I need to know that the square root of 34 is really close to 6. So when I plot the points, I'm going to go to almost 6 units up and almost 6 units down. So from this center point, I go down 1, 2, 3, 4, 5, almost 6. Square root 34. Watch out for gravity. That's it. Piece of cake, right? One thing I want to talk about real fast. Let's say this is what my rectangle looks like. And you got asymptotes here, and you got asymptotes here. And this one opens up sideways. So that would be a vertex, and this would be a vertex. I want to talk about what I'm expecting from you with your picture, what it should look like. When you draw these things, they do not go like this. They don't come backwards and then come along the asymptote. You should never go inside the box. The vertex is always the farthest over point. So they don't go like that. They don't go like this. Not a point down there. They don't go straight sideways and then come over. What they do is start from there and curve nice and gently along the asymptote. Oh, and they don't go like this. Guaranteed there will be some of you on your paper, when you draw your hyperbola, I'll do this on your paper. And what that's showing you is, look at how close the line is to, or the curve is to the line, the asymptote, and then look what happens to it. You're getting farther and farther and farther away from the asymptote. An asymptote is the line you get closer and closer and closer to. That's getting farther and farther away. Almost guaranteed, no matter how many times I seem to say that, people will draw it like that. Get closer to it. So this final picture should look something like this. Okay? Oh, I knew I had that somewhere. All right. So don't do any of these red things. Don't go straight sideways. Don't go backwards. Don't get farther and farther away from it. Should look like the blue one. One homework problem tonight. This one. Go.